This video lecture is meant to cover the information found in Unit 13 on gas laws, Objectives 3 and 4, which say you're going to describe how kinetic molecular theory applies to the behavior of gases, and to describe how pressure, temperature, and volume of a gas vary if one quantity is changed. This information can be found scattered throughout Chapters 13, Section 1, Chapter 14, Section 1, and Chapter 14, Section 2. We're going to take a look at the qualitative relationships of pressure and volume in a gas. And what that means is we're just going to try to understand conceptually what happens if you change the pressure of a gas, what happens to the volume, so long as we keep temperature constant. In this first simulation, we are going to take a look at a container that contains a fixed quantity of gas, and we are going to change the pressure on that gas and see what happens to the volume while we hold the temperature constant. So what we have here, temperature's at 300 K, the pressure's at 1 atmosphere. We're going to add a weight to the piston. Okay, and you can see that the dial here, shown next to the blinking arrow, that the pressure is going up. So the pressure is doubling to 2 atmospheres. The temperature remains the same, but the volume has been cut in half. So here we've seen a doubling of pressure results in the volume being cut. In this simulation, we saw that if you have a fixed quantity of a gas at 300 Kelvin and 1 atmosphere of pressure, if you then increase the pressure of the gas by putting this weight on top of the movable piston, what you end up seeing is that with an increase in pressure, in fact the pressure increases to 2 atmospheres. With the temperature remaining constant, the volume is cut in half. This is a law that we call Boyles Law. And effectively, if we conceptually consider what happened, with an increase in pressure, there was a decrease in volume with the temperature remaining constant. In fact, it was very quantitative. We could add a quantitative aspect to this. When we doubled the pressure, the volume was cut in half, so by the same factor. This is what is called an inverse relationship, and graphically it would look something like this. If we consider a point here, this is a large volume but a low pressure. If we look at a point up here on the graph, that's a high pressure but a low volume. So this is what we call Boyles Law. It's an inverse relationship between pressure and volume. If you take a container of Pringles in a vacuum pump, and we're talking about the single serving kind of Pringles, if you put them under low pressure, so that the area outside here is low pressure, which means the pressure inside the container is higher than it is outside. It's the pressure of the molecules inside, the gas molecules in here, that push open the container. All right, and so what we have here is the low pressure outside here allowed the volume inside the container to increase. So there you have it, Boyles Law with the Pringles container. All right, we're going to take a look at the conceptual relationship between temperature and volume with the pressure remaining constant. So in this particular relationship, we're going to heat up a fixed quantity of gas and see what happens to the volume. In this simulation, we are going to see the effect of when we heat up a fixed quantity of gas, what that will do to the volume of the gas while we maintain pressure to be constant. So here we see that the temperature of this gas is 300 Kelvin, the pressure is 1 atmosphere. We heat up the gas to 600 Kelvin. That's a doubling of Kelvin temperature, doubling of the kinetic energy, and that has doubled the volume. So doubling the temperature doubles. So in this simulation, we heat up a fixed quantity of gas. The initial temperature is 300 Kelvin. The initial pressure is 1 atmosphere. If after we heated up the fixed quantity of gas, the temperature doubled and the volume doubled. Notice the pressure remained the same. So in Charles's law, we say that with an increase in temperature, the volume will increase by the same factor so long as pressure is constant. This is what is referred to as a direct relationship, and graphically it would appear like this. If we consider a point out here on the graph, this is a high volume and a high temperature, and a point on this part of the graph would be a low volume and a low temperature. In this video clip, we're going to see balloons being placed into liquid nitrogen. Of course, you know the liquid nitrogen is very cold compared to the room temperature, and the balloons represent a fixed quantity of gas inside the balloon. So we're going to see what happens to the volume of the balloons as the temperature of the gas inside gets colder. You know, I know you've seen this in class already, but it's still worth seeing again. This, you get a different perspective from what you saw in the demonstration in the classroom. So here you can see that the balloon volumes go down dramatically. So with a very low temperature, there is a very low volume. So again, this is a direct relationship. You can see it here as the temperature increases, the volume also increases. And so there you have it. Everyday object and Charles's law. We're now going to take a look at the qualitative or conceptual relationship between temperature and pressure with the volume remaining constant. This is referred to as Gay-Lussac's law. In this simulation, we are going to see the effect of increasing the temperature of a gas, what that will do to the pressure of that gas if we keep the volume constant. So here we are heating up a fixed volume of gas. We are not allowing the size of the gas to change. We have doubled the temperature from 300 to 600 Kelvin, and that has changed the pressure from 1 atmosphere to 2 atmospheres. So doubling the temperature will double the pressure. In this simulation, what we have is, notice that the container does not have the movable piston anymore. We have the temperature reading initially at 300 and an initial pressure of 1 atmosphere. After the substance is heated, the temperature doubles, the pressure doubles. So here when you have a volume constant, but temperature increases, the pressure will also increase by the same factor. Right? So this is again another direct relationship, and it will be graphically represented the same way that Charles's law was. Okay? So Gay-Lussac's law, another direct relationship. And let's see what we can, we'll have another video clip for you to show you another everyday object and how it is affected by Gay-Lussac's law. You might have seen this video clip before. It is from Mythbusters.
The buildup of steam under pressure can cause many things to go off. But how about a water heater bursting right through your house? To mimic a real-life situation, the roof of the house has been constructed to California Building Code specifications. And the water heater contains no explosives. They turn on the power, hunker down, and wait.
You feel ready? Everyone's in position? Cameras are all rolling?
Yeah. We've got a nice little red house out there sitting now, you know, like everything's rosy.
Rosy on the outside, but roasting on the inside.
Okay, everybody, we're at 300 PSI. That's twice the tank rating. Keep your eyes peeled.
As the pressure inside the tank mounts, so does Jamie and Adam's heart rate.
315 PSI.
Oh, this is killing me.
320.
Any second.
325.
This is excruciating. This kind of stress on a regular basis can't be good.
No, shortening our lifespan.
We're going to make it 350. Oh!
Suddenly, the heater launches and tears through the roof like it's tissue. You could practically have a 3-course meal while you're waiting for it to come back down.
Look at the house. What house? I don't see a house. I don't know what you're going to be talking about.
This actually surprised me. The house was no hindrance whatsoever to the rocket. It probably would have gone through several houses like this before it stopped going.
It's like a fairy tale come true. The water heater huffed, it puffed, and it blew the house down.
It just goes to show you, you know, there's danger everywhere. Did you know what was lurking in your basement?
The guys inspect what's left of their once charming home.
The bottom of the tank went from concave to convex, probably in a split second. There's a hole in the roof. It had to go through 2 layers of 2x4 trusses in order to make that hole, and yet it totally did. And it did it without breaking any of the 3 windows in here. That's a rocket, my friend.
Yeah.
Not a bomb.
The trajectory and form of the 500-foot-high rocket-like blast is revealed on the high speed.
I gotta say, it's more interesting than an actual explosive explosion, because the steam is just erupting everywhere and completely disintegrating. It's different. It's more elegant.
Yes, it was like a lovely, delicate water heater ballet.
So that Mythbusters video shows you what happens when you have a water heater, which is a fixed volume of a gas inside. And of course, there's water in there, liquid water in there too. But when you heat up an enclosed container, the importance of having a pressure release valve, because if you don't allow the pressure to bleed off, then the pressure will get so high that when you heat up the water that it will actually eventually explode. All right, we will meet back in the classroom and put some numbers to these conceptual problems. See you in the classroom.